Okay, this is where we left off during our last lecture, was question 21.26, which asks us to identify the reagents that you would use to produce each of the following compounds using alkylation condensation. We're going to start with B, and this is a beta keto ester. You see that we have an ester here that would make this our alpha carbon and this our beta carbon, and you can see that there's a ketone on here. So again, a beta keto ester. And what we talked about last class is that when you think about this in terms of retrosynthesis, you would want to break this bond right here. And so our starting material, our starting ester, is going to come from this portion of the molecule. And so we can start by drawing that ester, which is ethyl propanoate or ethyl propionate. And the first thing we're going to do is we're going to treat that with lithium diisopropyl amide because it's a strong enough base to completely form the enolate. Now I'm going to remove the negative charge for that enolate because we know that that's going to completely be converted to the enolate after treatment with LDA. And now we need to decide, well, what's our electrophile going to be? And our electrophile is going to come from this portion of the molecule right here. And so the electrophile that we would put in, or we would add dropwise to the enolate, would look like this. So it's going to look like this. And of course, we want it to be an ethyl ester. And then finally, in the last step, once you've done the addition of the electrophile, right, you're still going to have some base in solution, and that's going to deprotonate to give you this doubly stabilized enolate. And so that's why the last step has to be the addition of aqueous acid. So we add aqueous acid to that, and we end up with our product like that. Well, let's take a look at another question. This is question 21.27. It says, predict the product of the Dieckmann cyclization reaction that occurs when each of the following compounds is treated with sodium ethoxide followed by acidic workup. So that means the first step, we're going to treat it with sodium ethoxide. And in the second step, we're going to treat it with acidic workup. So we're going to add aqueous acid to that. Well, we know that in these esters, and you can see that there's symmetry in this molecule, right? We know that there are 1, 2, 3, 4 acidic protons. Okay, I'm just going to leave one of them in for instructional purposes only. And it doesn't ask us to draw the mechanism, but it might be helpful here to say, okay, well, I'm going to have ethoxide, which is going to partially deprotonate, right? It's going to partially deprotonate. So it's not going to completely deprotonate that. But what I'm going to end up with is I'm going to end up with this enolate. So let's draw out the enolate, which is going to look like this. Okay, so I have my double bond, my ethyl group. And now what you see is that in the molecule, I have a nucleophile and I have an electrophile all in the same molecule. So I'm going to get a nucleophilic attack like this to form a tetrahedral intermediate. So let's draw what that tetrahedral intermediate would look like. I'm going to have my 6-membered ring like this. And now I'm going to have a, count with me, a 1, 2, 3, 4, 5-membered ring. So we'll add a 5-membered ring here. 1, 2, 3, 5, like that. On this carbon, my ethyl ester is still intact, but on this carbon, I'm going to have an oxygen with a negative charge, and I'm going to have this ethyl ether portion here. And so what's going to happen next is I'm going to lose that leaving group, which is going to end up giving me something that looks like this. Now, if you look at the solutions manual, it's going to tell you that this is the final product. So if you wrote this down as the final product, which I'm trying to finish up here, here we go. If you wrote that as the final product, right, that would be 100% correct. But what I want you to understand is that the mechanism is not complete at this point, right, because you just lost ethoxide. And when you lose that ethoxide, it can remove this proton here. And I mean, that's the proton it's going to remove because it's the most acidic proton in the compound. And you should be able to identify the most acidic proton in the compound. And so what you're going to do is you're going to deprotonate to form a doubly stabilized enolate. And in fact, that is the driving force of the reaction, is the formation of that doubly stabilized enolate. So let's draw that out. Here we go. It's going to look like this. Now I'm running out of space here, like that. Okay. And then in the last step, you're simply going to treat that with aqueous acid. So I'll kind of add the second, this will be the first step. And then the second step, you're going to treat that with aqueous acid like that. And then you're going to protonate. And so you'll end up with this as the final product, just like that. Okay. Well, in the interest of time, why don't we keep moving forward? And if there's time at the end of the lecture, we'll come back and we'll take a look at 21.27c, which is very much in the same vein as question B. But let's move on to a new section. It's a new day. So let's start with a new section. And the section is 21.5, alkylation at the alpha position. It says the alpha position can be alkylated when an enolate is treated with an alkyl halide, right? The first step that's being presented here is nothing new to you. You know that when you treat this, this ketone, cyclohexanone, with LDA, you know that at the alpha carbon, we have 2 acidic protons in this case. And if you're wondering, could you have drawn them on this side? Yeah, absolutely, right? There's symmetry in the molecule. I'll just draw, you know, those 2 in for instructional purposes only. What you're going to do is you're going to remove one of those protons, and you're going to end up with the enolate. That's after the first step. So what's going to happen in the second step is shown down here, is that that enolate is going to attack the alkyl halide via an SN2 reaction. So you can see that we have alkylation occurring at the alpha position, and that's what the title of this section is called. So we're going to explore this reaction in detail. Well, you probably noticed that the second step here is an SN2 reaction, and the typical, you know, restrictions that apply to SN2 reactions are going to be observed here, that when a secondary or tertiary alkyl halide is used, that we're going to end up with E2 as the predominating reaction mechanism. And so also the aldol reaction also competes with the desired alkylation. And so a strong base such as LDA must be used. What this bullet point here is telling you is nothing more than this, okay? It's nothing more than this. All it's saying in that second bullet point is that for the first step, you couldn't use, you know, an alkoxide base. Wouldn't work, okay? Why wouldn't that work? Okay, it's not going to work because you'd get partial formation of the enolate, and then you would just get an aldol reaction, okay? So that's not really going to be helpful at all. So that's all that second bullet point is saying. And then the last bullet point on this slide says regioselectivity, though, can be an issue. In that case, we could form 2 different enolates. And so the question becomes, you know, which one is going to predominate and when will it predominate? Here we go. Here's an example where they're showing you start out with this alpha substituted cyclohexanone. So we already have this substituent here, and we have, you know, we have an acidic proton here. But on this alpha carbon, we also have an acidic proton here, and their pKa's are going to be extremely close. So if we were to treat that with a base, okay, an alkoxide base, let's say, you know, which one of these enolates is going to predominate? Well, the answer is here. It says that under thermodynamic conditions, what is called the thermodynamic enolate will predominate. Now, what's thermodynamics, you know, governed by? It's governed by the stability of the final product, or the product, I should say. And so in this case, we end up with a more stable enolate. Why is this enolate more stable than the enolate that's shown over here? Simply because the double bond is tetrasubstituted, right? This double bond is tetrasubstituted. Whereas the double bond over here, if I was to remove the proton in red, this one is trisubstituted. And remember, when we looked at alkenes way back in chapter 7, we said that the more substituents we have on a double bond, the more stable that double bond becomes. And so when we deprotonate to form the more stable enolate, we call that the thermodynamic enolate. And when we deprotonate to form the less substituted enolate, we call that the kinetic enolate. And so you have to know the difference between a thermodynamic enolate and a kinetic enolate. Well, although the thermodynamic enolate is more stable, you might think, okay, well, that's the only one I'm ever going to form. The answer is no, because the kinetic enolate is in fact formed faster. Now, why would it be formed faster? The only reason that the kinetic product is going to be formed faster, so kinetic would result from the deprotonation or removal of this proton here, right? That's going to give us this one here, okay? The reason why is simply because it's less hindered, okay? less, maybe I should try to be color coordinated here. So this proton is simply less hindered, and so it's going to be pulled off, more rapidly, even though the enolate is less stable. Here's a reaction coordinate diagram showing the formation of the enolate. And if you look at the activation energies of these two enolates, okay, so if we have the activation energy, so we'll call this the activation energy of kinetic, okay, and we'll call this the activation energy of our thermodynamic product. You can see that the activation energy of the thermodynamic product is higher, even though the product is more stable, okay, or the intermediate, I should say, is more stable. And so the question becomes, how do I get the reaction mechanism to do what I want? What if I want to alkylate at the less hindered position? Well, you can imagine that you're going to use less heat, right? You'd use a lower temperature because you don't want to, reach this spot in terms of activation energy, because then you're going to have an equilibrium, right? And then your product is going to, your enolate will equilibrate to give you the thermodynamic product. And really what you need to know is shown here. The kinetic enolate is favored by irreversible conditions. Okay, and what would those be? Those would be simply treatment with a strong base at a low temperature, minus 78 degrees. And if you're wondering, why minus 78, why wouldn't they round that off to minus 80? It's because when you make a mixture of dry ice and isopropanol, okay, that gives you a bath that is minus 78 degrees Celsius. And it's very commonly used in the organic chemistry lab. So we take our alpha substituted cyclohexanone, in this case, we treat it with LDA at low temperature, and we remove the less hindered proton, okay? And we call that the kinetic enolate. Now, again, that's irreversible, whereas if we were to do this reaction at room temperature with a strong base like sodium hydride, okay, so we're using sodium hydride at room temperature, 25 degrees Celsius, well, you're actually going to remove both protons. Now, it's not showing it here, but you're going to remove this proton and you're going to remove this proton. But remember, you're at a high enough temperature that you're going to have an equilibrium, right? You're going to form some of this and you're going to form some of this, okay? But this kinetic enolate is going to be reversible, and eventually it's all going to equilibrate to give you the more stable enolate. It's my little animation maybe on that reaction coordinate. So, the bottom line, or the take-home message as an Organic Chemistry 2 student, is that you need to know when you treat the unsymmetrical ketone, alpha substituted ketone, with LDA at low temperature, you're going to form the kinetic enolate, which is going to be the less hindered enolate, or the less substituted enolate, I should say. And when you treat it with sodium hydride at room temperature, you're going to form the thermodynamic product, and that is a result of the formation of the thermodynamic enolate, which is the more substituted enolate. Nothing more than that. Well, with that in mind, and I've taught this class long enough to know that most students simply memorize this. Let's tackle a problem here. It says, for each of the following reactions, predict the major product and propose a mechanism for its formation. The first one, we're treating it with LDA at minus 78. We got two types of alpha protons here, right? We got this one here, the red one, and we've got this one I'm going to highlight in blue. Who could tell me which one of these is going to be removed preferentially with LDA at minus 78? It's not a trick question. I'm going to draw my LDA like that. Yeah, it's going to be the blue one because it's the less hindered proton, and we're at minus 78 with LDA. So we're going to form this intermediate, which is going to look like this, okay, like that. All right, so there's our intermediate. And then in the second step, we're going to treat that with iodomethane. So let's draw the Lewis structure of our iodomethane. We get an SN2 reaction, bada boom, bada bing, and we end up, making a longer carbon chain right there. Okay, the second one, we have, again, two types of acidic protons. We have this one here in red, and then I'll put this one here in blue. Who could tell me which one of these ones would be pulled off or would eventually be form the preferential enolate? Would it be the red one or the blue one in this case? Exactly, it's going to be the red one. Exactly, because that's going to form the more substituted enolate. So we're going to remove that red proton like this. We'll draw our enolate. It's just going to look like this. I'm going to draw it the other way around just so I can draw a prettier reaction mechanism. Okay, so now I've got my enolate after the first step. And in the next step, I'm going to treat that with benzyl bromide. Benzyl bromide, and there we go. We're going to get a nucleophilic attack like this, SN2 displacement. And let's draw what our final product will look like. We have a methyl group, CH2, and our phenyl. And there you have it, folks. There we go. So the first reaction gave us what we call the kinetic product. And this product is the thermodynamic product. Thermodynamic product. Okie doke. Well, let's move on from there. Let's talk a little bit more about alkylating at the alpha position of an ester. The malonic ester, at an ester, the malonic ester synthesis, sorry. Yeah, still got ketones on the brain. Anyhow, we're going to learn a couple of new syntheses this morning. We're going to look at the malonic ester synthesis, and then we're going to look at a synthesis with ethyl acetoacetate in a few minutes. But this first one, the malonic ester synthesis, which is a brand new reaction you need to know, malonic ester synthesis, is where you take an alkyl halide and you convert it into a carboxylic acid with 2 additional carbons. Now, we need to really look at these carefully. These are the 2 additional carbons, right? Everything else came from the R group. So you have 1, 2 additional new carbons, and then we have a carboxyl. And the way that we do that is we start it with diethyl malonate, which is this compound right here. You can see that it's just the diethyl ester of malonic acid. Remember, we learned malonic acid way back, in chapter 19. So diethyl malonate is the starting material. And first we react that with a base to form the corresponding enolate. Now remember, this is from the first lecture in this chapter, that when we take an enolate and we end up with a doubly stabilized enolate, that when we deprotonate with sodium ethoxide, it's going to be a complete total deprotonation, right? Because the pK of that proton that's being removed is around 9. Okay, and again, that's something that we looked at during the first lecture. Now, you could already see what's going on here. We have this doubly stabilized enolate, and we're going to react that with what? An electrophile. So let's take a look at what that appears like over here. So we take that enolate, we treat it with the alkyl halide, right? You can clearly see that this is nothing more than just a plain old everyday SN2 reaction. And then after that, you treat it with acid, okay? Now remember, when you take an ester and you treat it with aqueous acid, that produces a carboxylic acid. This is nothing more than the acid catalyzed hydrolysis of an ester. Now here's the cool part, okay? You've got this 1,3 dicarboxylic acid, 1,2,3 dicarboxylic acid. This is unstable, okay? Unstable. Because you remember that our product only had 1 carboxyl group. Are you ready to see one of the neatest mechanisms you'll learn in this class? Where is it? I'm going the wrong way. It's this one right here. So if you take that dicarboxylic acid and you heat it up, you end up losing CO2, and you're only left over with 1 of the carboxyl groups. So here's the mechanism of that process right here. 1,3-dicarboxylic acids undergo decarboxylation in a pericyclic process. So all you have to do is take this portion of the molecule and kind of flip it around, right? You just kind of rotate on this bond here, and then you draw out the oxygen-hydrogen bond explicitly. And you can see that it's a concerted process, right? Happens all in one step, and you end up losing CO2. So the carbon dioxide comes from these 2 oxygens and this carbon, and then we end up forming an enol, which undergoes tautomerization to give us the carboxylic acid. Pretty cool mechanism. One of the coolest mechanisms that we look at, and if you like it, good news is that we're going to see it again later. So you probably noticed the last few slides kind of breaks this down into step after step after step. Here's what it looks like when you put it all together. So you buy some diethyl malonate, right? You purchase that from some kind of supplier, right here. Here's your diethyl malonate. You buy that. It's a liquid, comes in a bottle. Okay. So you measure that out. Then first you're going to add your sodium methoxide to give you the doubly stabilized enolate, right? That's after the first step. And then that's going to work as a nucleophile and do a nucleophilic attack on your electrophile. Okay. Then all you got to do is hit it with acid and heat it up, and you decarboxylate, or you lose carbon dioxide, and you end up forming a carboxylic acid with 2 new carbons. If you can't remember all that, here's a kind of the quick and dirty way to do it, right? You're going to take this compound right here. What are you going to add? You're going to add 1, 2 carbons to it, and you're going to have a carboxyl group on the second carbon. Okay, that's kind of a quick and dirty way of doing it, but hey, if it works, right? Another option is you can dialkylate, right? Because there are 2 acidic protons here, right? 1, 2. So after the first deprotonation and alkylation, you do a second deprotonation and alkylation. It's important that you know here that with this, order not important, okay? You can do them in whatever order you want. Doesn't matter a hill of beans, okay? So if the book says the first one, the second one, and you do it the other way around, no problem, okay? Not a big deal at all. Well, with that in mind, let's propose an efficient synthesis for each of these compounds using the malonic ester synthesis. These are really great questions to enhance your retrosynthetic strength, I guess. Okay, well, let's think about this. Look, we have a carboxyl group here, and here we have the last 1, 2 carbons. So that means our starting material is going to come from what? It's going to come from all of these carbons here. Okay, so that's going to be where our alkyl halide is going to come from. Our alkyl halide is going to come from those, 5, 6 carbons total. Okay, so what are we going to start with? Well, we're going to start out with diethyl malonate. So let's draw that out. Okay, in the first step, we're going to treat that with sodium methoxide, always the same thing to deprotonate. Then in the second step, we're going to treat it with our alkyl halide, and it's going to come from what's inside that yellow box, right? It's going to look like this. It's going to have a 5-membered ring. It's going to have a carbon, right? That's this carbon, and then it's going to have a halogen attached to it. Choose whichever one you want. Let's choose iota. We're going to break the bank, okay? And then in the third step, you're just going to hydrolyze it with acid like that, and that will give you the desired product. Let me ask you guys a question about the second one. You can see again that we have 1, 2 carbons. So how many alkylations will I have to do in this problem? Will I have to do 1 alkylation or 2 alkylations? And it's not a trick. Yeah, dos. See, you're going to have to do 2 alkylations, right? You're going to have to add this group that I have in red, in the red box, and then you're going to have to add the ethyl that's in the blue box. So again, same thing. Look, I'll even take the copy paste tool. Look, I'm going to copy and paste the first 2 steps in the malonic ester synthesis. So copy, come on, paste. There we go. Okay, so let's add the first electrophile. The order is not important. Let's start with what's in the red box. So we're going to put this guy, okay, like that. The third step is going to be another deprotonation. Okay. The fourth step is going to be to add the ethyl group. So we'll put ethyl iodide, just for fun. Okay, what would that give us? Let's draw what the intermediate would look like since I didn't do it in the first problem. It's going to look like this. Here's my diethyl malonate, but now instead of the 2 hydrogens, right, instead of these 2 hydrogens, what am I going to have? I'm going to have an ethyl group on one side, and I'm going to have this group on the other side, like that. Okay, so what's the last step going to be? It's going to be to treat that with aqueous acid, and we end up with our product, like that. All right, so we had an ethyl and an isobutyl group, and there you go. Hydrolyze it, and bada boom, you're off to the races, my friend. Give me a thumbs up if you think you could do that. Just, I need to memorize the reagent, diethyl malonate. Okay, great. Good, so good. All right, well, let's move on from there. Here's another sort of analog of the malonate synthesis, which is called the acetoacetic ester synthesis. You know, try that one on for size. The acetoacetic ester synthesis. We start with this molecule here. This is called ethyl acetoacetate. Ethyl acetoacetate. So it's kind of like diethyl malonate, but you're missing this ester group over here, right? So we'll delete that. And that's ethyl acetoacetate. And as you can imagine, the mechanism is identical to what we saw before. Even the decarboxylation step is the exact same. What's the difference here is that now you're adding 3 new carbon atoms and you're making a methyl ketone. Okay, so you're making a methyl ketone, right? This is clearly a methyl ketone, and we have 1, 2, 3 new carbons like that. Pretty cool, huh? All right. Well, let's try a problem where we would use the acetoacetic ester synthesis. Look, again, exercising our retrosynthetic prowess. Look, we have a methyl ketone, clearly. Here we have a methyl ketone. Let's count back. 1, 2, 3 carbons. So those are going to come from our starting material. So that means our alkyl halide is going to come from this portion of the molecule. Excuse me. So let's write what we're going to start out with. Our ethyl acetoacetate. So we'll draw that out in detail like this. The first step is going to be to treat that with sodium ethoxide. What's that going to do? That's going to deprotonate to give me a doubly stabilized enolate, right? So when we do that, in the second step, we're going to treat it with what's inside that, that black box. And let's draw what our electrophile would look like. It's got a 6-membered ring, and it's got, you know, bromo or chloro or iodo. It's not important what you put there, but do what you feel, right? Come on. Thought this would be faster than erasing it. There we go. All right, so we get our SN2 reaction like that. Then what are we going to end up with? Let's draw the whole darn thing here. So we're going to end up with this intermediate, which looks like this. Okay, we're going to have our cyclohexyl group here like that. And the next step, we're going to treat that with aqueous acid. Cha-cha. So it's going to look like this. And we're going to have this, and this, and this. Come on. There we go. And this guy, put that back here. And then we can draw our pericyclic mechanism, which shows the decarboxylation, like that. I'm really running out of space here, but you can see how we're going to lose CO2, and then we're going to end up with this enol, which is going to tautomerize to give us the final product, which will be, no, I can draw the enol, can't I? I got room. Let's draw what the enol looks like, which looks like this. I should fix this arrow. It should look like this, actually, like that. Yeah, let me draw my enol. Where was I? Where's my black pen? Come on. So I'm going to have this enol. There we go. So there's our enol, and that's going to undergo tautomerization to give us the final product, like that. Okay, again, in the interest of time, why don't we just skip over this one, 21.33b, and if we have time, we'll come back and do it, and I think we will. I'll write it down here, 21.33b. Okay, so acetoacetic ester synthesis and malonic ester synthesis, 2 brand new syntheses. You always got to be on the lookout for, you know, the portions of those molecules that are formed, you know, the methyl ketone or a carboxylic acid where you add 2 carbons. All right, well, here is the last section of new reaction, section 21.7, if I'm correct, and I'm looking through my notes here. Yeah, question 21.7 just deals with synthesis strategies. So section 21.6, last section of new chemistry, It's called conjugate addition reactions. Recall that an alpha-beta unsaturated carbonyl is made via an aldol condensation. And we said the conditions for doing that were what? Sodium hydroxide in water, and we heated it up, right? And that drove the E1CB reaction, and we made a conjugated system, right? Well, if you look at the resonance contributors for that alpha-beta unsaturated aldehyde, you can see that there are actually 3 resonance contributors, and 2 of them where we have positive charges on carbon. What does that tell us? That tells us that those 2 carbons that I can have kind of highlighted in yellow, those are both electrophilic carbons, right? This carbon is electrophilic, and this carbon is electrophilic. So if we were to attack that alpha-beta unsaturated aldehyde with a nucleophile, where's it going to attack? Which one of those electrophilic carbons? Well, the answer is it depends on the nucleophile used. Again, this slide just summarizes what I just said. The beta carbon and the carbonyl carbon are both electrophilic. And where the nucleophilic attack occurs is going to depend on the nature of our nucleophile. Well, first let's take a look at what would happen if you were to hit it with a Grignard, okay? So you just take that plain old alpha-beta unsaturated aldehyde and you hit it with, I don't know, methyl magnesium bromide, okay? Now here they're just giving you a generic R group, okay? So you're hitting it with a Grignard, and what it's telling you is that what you end up with is called 1,2 addition, and it's the result of nucleophilic attack at the carbonyl, right? And you can even draw the mechanism out if you want. So the Grignard is going to attack here, right? And then you would protonate that, and we call that 1,2 addition. Now the reason we call that 1,2 addition is the following, because the carbon where the nucleophile attacked, that's the 1 position, and where the hydrogen was added, that's 2. So we call this 1,2 addition. Okay, so that's with a Grignard reagent, and you have to have that memorized. With a Grignard reagent, you're going to get 1,2 addition. But if you treat it with a Gilman reagent, right, a dialkyl lithium cuprate, what would happen in that case? A Gilman reagent is actually going to attack at the beta position, right? This is the beta position here. Here's the alpha position, and this is called conjugate addition or 1,4 addition. Now, if you look at what's being added overall, right, you see that you added this R group, and then you added a hydrogen here, right? There was already a hydrogen here, and you added a second one. Okay, so that kind of looks like it would be 1,2 addition, doesn't it? But in fact, it's 1,4 addition. All right, and the reason why is shown on this next slide here. Okay, because when you draw out the mechanism of conjugate addition after your nucleophilic attack, you form an enolate, and that enolate gets protonated, okay, to form an enol. So in fact, what you have is 1, 2, 3, 4. You added something at the first carbon and something at the fourth, or the first atom, I should say, and the fourth atom in this system. Okay, that's undergoing the reaction. And so we call that 1,4 addition. The reason it looks like 1,2 addition is because of what? It's because of tautomerization of the enol to produce the aldehyde in this case. Okay, so conjugate addition. Conjugate addition, you guys, is extremely important in organic chemistry. Very powerful chemistry. Making new carbon-carbon bonds is always, you know, whenever there's a reaction that involves carbon-carbon bond formation in organic chemistry, you can bet your bobby socks it's going to be really important. So here we go. Stronger nucleophiles like a Grignard. So stronger nucleophiles like a Grignard are going to do 1,2 addition. Less reactive nucleophiles, we'll say a Gilman or a cuprate, is going to do the conjugate addition. Now, what about enolates? If you were to take a typical enolate, right? Let's say you took, this enolate, okay? What's that going to do? Where's that going to attack? Well, the problem is you usually get a mixture, okay? You're going to get a mixture of 1,2 and 1,4 addition, which, mixtures, sometimes in organic chemistry, you just got to bite the bullet and say, hey, I get a mixture, I'll separate it out and I'll move on with life. Other times you don't want that, you want to get either the 1,4 or the 1,2 to predominate. And when we use a stabilized enolate, and what a stabilized enolate means is if we had this, 1,3 dicarbonyl, right? you know that that's a doubly stabilized enolate, right? I could put the negative charge here or here. So we call that a stabilized enolate, and if we use a stabilized enolate, what we get is conjugate addition. What we get is conjugate addition exclusively. Let me go back to my slide, which I lost. Where was it? Here we go. Again, the stabilized enolate gives 1,4 addition, or that's, and again, that's the same thing as conjugate addition. Come on. Addition, like that. I don't know if I've mentioned it today. I don't think I have. But conjugate addition means that the nucleophile is being added to what? A conjugated system where you have double, single, double, right? That's a conjugated system. So that's where the name conjugate addition comes from. I know it's mentioned in the textbook, but I may have neglected to say that along the way. What's happening in this reaction at the bottom is that first you're going to deprotonate, form that stabilized enolate. So we could draw that stabilized enolate. Come on. I'll start by drawing a lone pair here in our negative charge, and that's going to do a nucleophilic attack like this, okay? And then you're going to protonate that to form an enol, and then it's going to undergo tautomerization to reproduce or regenerate the aldehyde. The conjugate 1,4 addition, so 1,4 addition or conjugate addition, it's got another name, and this is what most organic chemists would use. If you were talking to somebody, you know, if you're a bench chemist like I was for most of my adult life, you'd call that a Michael reaction. You'd say, oh, I did a Michael reaction. And the Michael donor is the nucleophile, and the Michael acceptor is the alpha beta unsaturated carbonyl. So this would be, come on, this would be the Michael donor, and then this here is the Michael acceptor. Okay, so Michael reaction. Sometimes, I don't know, I call it Michael addition, which probably isn't correct, but anyhow, sometimes I call it that. Just a Michael reaction. Okay. Anyhow, the following Michael donors give exclusively 1,4 addition with an unsaturated carbonyl compound. There we go. So you need to have this list of Michael donors memorized, okay? Now, you might think, oh, come on, just more things for me to memorize. Well, the only one on there that I would say is kind of the outlier, it's not even an outlier, would maybe be the Gilman reagent, right? Because you think, okay, well, Gilman, you're not going to draw the doubly stabilized enolate where you can in all of the others, right? You should be able to do that with all of the others here, even with this, you know, nitrile here and with this nitro group there. Okay, so those are examples of Michael donors, and Michael acceptors are basically alpha beta unsaturated carbonyl compounds, whether it's an aldehyde or a ketone or an ester or an amide, and also an alpha beta unsaturated nitrile or a nitrile and nitro. Okay, so those are the things you want to keep in mind. And what we're going to see later on in this chapter is that an enamine. You guys remember enamines? Yeah, we looked at enamines in detail earlier on. So let's draw this like this and say an enamine could be, come on, enamine could be thrown into the ring. Okay, well, let's take a look at this question, which says predict the major product of the 3 following steps and show a mechanism for its formation. I'm going to try to draw a condensed version of the first step, which is just the deprotonation. I'm sure you can all draw that in your sleep by now. So we'll draw the base, our hydroxide. We'll draw the deprotonation like that, and we form an enolate. Okay, so let's draw the enolate out. It looks like this. There we go. And then so that's going to be our Michael donor. We could write that down. This is our Michael donor. Okay. And then our Michael acceptor is going to be the alpha beta unsaturated ketone. So let's draw that out. Go. Let me fix up my double bond. Hopefully you guys are following along here and trying to draw these mechanisms. You probably draw them faster than me. Okay, so this is our Michael acceptor. Just write acceptor here, and we're going to get our nucleophilic attack like that. And we're going to end up with an enolate. So let's draw what that enolate would look like. Put in our carbonyls. So what have we got here? We've got 1, 2, 3 carbons. So 1, 2, 3 carbons, and 1, 2, 3, and then we have our 6-membered ring. Let's draw that. Then we're going to have our double bond here. Or draw our enolate. Come on. I really need a new prescription. Okay. There we go. And then in the next step, we're simply going to protonate that with hydronium. So I'll draw my hydronium on kind of like this. Sort of a shorthand for it. Like that. It's missing a lone pair, isn't it? There we go. So we're going to end up with the enol. Let's see if I can draw that with the space that remains. In organic chemistry, it's always good to have lots of paper. The good news is paper is cheap. Very cheap. So here's the enol. Okay, and then that is going to undergo tautomerization to give us our product. So let's draw the product out. It's going to look like this. 1, 2, 3. And my 6-membered ring. Like that. And my carbonyl. There you have it, folks. So that's the mechanism for the Michael reaction. All right, and everybody should be able to draw the mechanism of the Michael reaction. 21.37, using diethyl malonate as your only starting material, or as your starting material, I should say. So diethyl malonate, remember it's this guy. It's just the ethyl ester of malonic acid. And any other reagents of your choice. Show how would you prepare each of the following compounds. So we're just going to make this compound. Let's see. Oh, I see what they're getting at here. The problem with this, if you think about diethyl malonate or the malonic ester synthesis, right? You think, okay, well, I've got 1, 2 carbons here. I could get that from my diethyl malonate, right? That would come from, come on, it would come from this part of the molecule. The problem with that is that's an SN2 reaction, right? That's an SN2 reaction. So if you think retrosynthetically, you would start with diethyl malonate and what? You'd have this. You'd have this guy like this. Okay, and then you'd have to have a halogen here, let's say. Not going to work. Okay, that won't work. Will not work because this is a tertiary alkyl halide. And when I say will not work, I should put malonic ester synthesis will not work because it's a tertiary alkyl halide. So we got to think, what else could we do here? And what I would think of is that why couldn't we do conjugate addition, right? Why couldn't we do a Michael reaction and break this bond right here? Because then, in terms of our retrosynthesis, we could start with this alpha beta unsaturated ketone, right? And then we could use diethyl malonate as our Michael donor. And so what we would do then is we would start it with diethyl malonate. I'm going to run out of space here. Let me move this guy over here. So I'm going to fix this retrosynthesis arrow. Go like this, and then we'll go like that. Okay, so that's the technique or the method we're going to use. So let me show you what I mean. We're going to start with diethyl malonate, and we're going to completely deprotonate that using sodium ethoxide, right? Sodium ethoxide. So let's just copy this. So copy, paste. There we go. Then we're going to end up with our enolate. So let's draw that out. Okay, so that's going to be our Michael donor, and then our Michael acceptor will be this molecule that I had already drawn, the alpha beta unsaturated ketone. And so we get a nucleophilic attack like this. Okay, we produce our enolate, which we protonate next, and that gives us our desired product. So I could even draw the intermediate out here. Come on. And all that's gone. Okay. So let's look at the last sort of section of 21.6, which is the Stork enamine synthesis. And it's named after a chemist named Gilbert Stork. Because singly stabilized enolates do not give high-yielding Michael additions, right? We said that in that case, you get a mixture of 1,2 and 1,4 addition. Gilbert Stork developed a synthesis using an enamine intermediate. And remember that we covered enamine synthesis in section 19.6. So this is back in the carboxylic acids and their derivatives chapter. Or sorry, no, my mistake. That's in the aldehydes and ketones chapter. Jeepers. Aldehydes and ketones chapter. Anyhow, the way that we make an enamine is that we take a ketone. Okay, we take a ketone and we treat it with a secondary amine in a catalytic amount of acid, followed by the removal of water, and we end up with our enamine. And you can see how this would be how this could be a Michael donor, right? Because we could draw, a resonance structure like this, and you can see how that would behave as how it could behave as a nucleophile, and that's shown on this slide. Shown on this slide right here, you can see how an enolate has a negative charge on the alpha carbon, and how the enamine also has a negative charge on the alpha carbon in this resonance contributor right here. But overall, it has no charge, right? The enolate has a negative charge, whereas the enamine has no charge because the negative charge is balanced out by the positive charge on the nitrogen. And therefore, the enamine is less nucleophilic and makes a good Michael donor. Okay, so it's going to do conjugate addition. Now, here's the mechanism of the conjugate addition of the Michael donor. So we draw the negative charge on our nitrogen, and then we draw the conjugate addition reaction arrows. And then after conjugate addition, you end up with this intermediate. And this is a key step here that you know that all you have to do, or all you have to know, is that you end up forming an enolate and an aminium. And when you treat that with aqueous acid, it removes this and it removes this, and you end up with a ketone in both places. Okay. We already looked at the hydrolysis, or sorry, we looked at the conversion of an enolate to an enol and then tautomerization, but the aminium is just going to get hydrolyzed to the ketone. And so that's the last step of the Stork, of the Stork enamine synthesis. Where was I? So overall, here it is summarized. The three-part process is called the Gilbert Stork enamine synthesis. So first we take a ketone, treat it with aqueous acid, we remove water, we form the enamine. That's a Michael donor. We do the Michael addition, and then finally we hydrolyze the aminium, and we convert the enol, or the enolate, into the enol, and that undergoes tautomerization. The person that taught this class before I was hired by UCCS, he gave me all his notes. I don't use them, but I remember looking at his summary of this chapter, because this is the first class I ever taught at UCCS, was organic chemistry 2. And he said, one of the keys that you would want to look for is whenever you have two carbonyls that are separated 5 carbons apart, that would kind of be your given that you're dealing with the Stork enamine synthesis in organic chemistry 2. So whenever you have 2 carbonyls 5 carbons apart, and with that in mind, let's look at a problem where we see that very thing manifested in a problem. So 21.38, using a Stork enamine synthesis, show how you might accomplish each of the following transformations. And So it doesn't matter, I guess, really what the enamine that you form is. Let me go back here to show you what, no, it doesn't show any. Yeah. So what I'm saying is that for this step here, what are your R groups going to be? We're usually going to choose just dimethylamine, okay? Usually, we'll put usually dimethylamine, okay? Nothing fancier than that. All right, so we're going to start with dimethylamine in the first step. So we'll take this guy and we'll treat it with dimethylamine, a catalytic amount of acid followed by removal of water. And we're going to end up with this intermediate. Forgive me, there's not a lot of space here, but you're going to end up with this enamine. It's going to look like this. And then we need to treat it with our Michael acceptor. So what's our Michael acceptor going to be in this case? Well, let's count our carbons. Right? If we break this bond here, our Michael acceptor is going to come from this portion right here. Okay, and so our double bond is going to be at that position. So let's draw that as our Michael acceptor. It's going to look like this. We have our conjugated system, and then we have an isopropyl group on this side. Okay, so what that's going to do is that the enamine is going to behave as the Michael donor. We could even draw the curved arrows for this, like that. Okay, like that. And then we're going to end up with this intermediate. So that we're going to have something that looks like this. So in this position, we're going to have an iminium ion. And in this position, we're going to have our enolate ion. Right, overall, the molecule has no charge. And then in the last step, you're going to treat this with H3O+. All right, so the summary is that first step was to treat it with dimethylamine, aqueous acid, remove the water. The second step was to treat it with the Michael acceptor. And in the third step, we treated it with aqueous acid. Okay, let's try the next one. Kind of the trick in the next one is that this methyl group here is this methyl group that's pointing down like that, right? Because when you treat this with dimethylamine in the first step, right? If you treat this with dimethylamine, catalytic amount of acid, and remove the water, you end up with this enamine, which looks like this, which looks like that, right? So what's our alpha beta unsaturated ketone going to look like, right? We're going to have to break this bond here. And thus, in the next step, our alpha beta unsaturated ketone is going to be this guy, okay? And then that's going to give us this intermediate. We have our iminium. We have our enolate, which looks like this. Okay, and if you need some help on the curved arrows, you can just, first I'll draw in the lone pair on the nitrogen. Here we go. Like this and like this. Oops, I forgot my positive charge on my nitrogen. And then in the last step, we treat that with aqueous acid. Okay, storic enamine synthesis. Well, I guess there's one more reaction. I think, yeah, this is the last reaction that I promise this is the last reaction in the entire chapter. It's called the Robinson annulation reaction. And it's nothing more than two reactions that you've already learned. Okay, Robinson annulation, you can guess that annulation has something to do with making a ring. It's a two-step process for forming a ring. The first part is the Michael addition. We studied that in detail. And the second part is intermolecular aldol condensation. We looked at those in detail. So it's really just two reactions that we've already looked at. You can see that the starting material, right, is 2-methyl-1,3-cyclohexane dione. We have an acidic proton here. We treat that with sodium hydroxide. We're going to end up forming the stabilized enolate, which is going to be able to act as a Michael donor. We have a Michael acceptor here. Okay, so you can draw out all the steps for after the Michael addition, right? The first part is going to be, you know, treatment with sodium hydroxide. And then, of course, you're going to have to do some kind of acidic workup in order to isolate the ketone. And then you would take that and you would treat that with sodium hydroxide again. And that's going to act as a nucleophile. We have an electrophile in the same molecule. And then we're going to do our E1CB and do an aldol condensation to form an alpha beta unsaturated ketone like that. And that's the Robinson annulation. So two reactions that you've already looked at. Now, the only kind of question that I would ask you about Robinson annulation really is this sort of question here, where it says identify the reagents that you would use to prepare the following. So you think about this, here we have our alpha beta unsaturated carbonyl. So that's where you're going to want to start, right? You're going to want to start by breaking that bond. And if we break that, so let's think about our retrosynthesis. What would we have in that case? We'd have our aldehyde here. We have our methyl group. And over here, we'd have another aldehyde, right? That double bond is going to come from another aldehyde. And then we have 1, 2, 3 carbons, right? 4 carbons to our ketone. So we have 1, 2, 3, 4, like this. So this would be the intermediate that we would use for our aldol condensation reaction. And then if we think about this in terms of, you know, how would we make this material from a Michael addition, we would break this bond here, wouldn't we? Because then we could make a doubly stabilized enolate from this dialdehyde. Okay, with a methyl group here, right? We'd have, if we were to remove this proton in red, we'd have a doubly stabilized enolate. And then our Michael acceptor would come from all of this. Okay, our Michael acceptor would come from here. And we could write that down. So our Michael acceptor will simply be this guy. All right, there we go. So there we go. And so the reaction is it's asking us for what the reagents would be, excuse me, for this reaction. And the two steps don't represent two separate reactions. In fact, the Robinson annulation can be formed in one reaction flask. And so all you would have to do the Robinson annulation would be this. You would take your starting dialdehyde. Okay, so there's your dialdehyde. You would treat it with the alpha beta unsaturated ketone. Okay, and you would just treat it with sodium hydroxide, and you would heat that up, and that will give you the desired product, like that. And, you know, one of the kind of take-home messages of the Robinson annulation is it helps you appreciate how keen an eye a good organic chemist has to have. That they could just open up a journal and see this, you know, and say, oh, well, you would make that from a Robinson annulation, you know, without having looked at it, you know, recently. If it's a reaction you haven't even thought about for a year or 2 years, but you'd still look at that and say, oh, you know, that must be made from a Robinson annulation. All right, there we go. And that is all of the new chemistry in this chapter. Let's take a look at section 21.7 quickly. We got about 10 minutes left. Most of the reactions in this chapter are carbon-carbon bond forming reactions and yield products that contain more than one functional group. We looked at the aldol reaction and aldol condensation. So an aldol reaction gives you a beta hydroxy aldehyde or ketone, and an aldol condensation gives you an alpha beta unsaturated aldehyde or ketone. Claisen condensation is where we react two esters together, storic enamine synthesis, and we looked at the Michael reaction. We looked at the malonic ester synthesis, the acetoacetic ester synthesis. The positions of those functional groups in a target compound dictate what reactions can be used to synthesize it. That goes back to what I told you about, my predecessor who said in his notes, well, you just look at how far apart the functional groups are, and that should be able to give you some kind of strategy as to what synthesis you would use. So if we want to make a 1,5-dicarbonyl compound, we would use the storic enamine synthesis. Whereas if we want to make a 1,3, this shouldn't say difunctional, it should say bifunctional compound, I think. Anyhow, you would end up using either an aldol reaction or a Claisen reaction, both of which are shown here. What else? If we want to alkylate at the alpha position, we produce an enolate, either the thermodynamic enolate or the kinetic enolate. And this is something that I really wanted to show you, is that if you combine those two reactions, you can actually do a dialkylation. So what would happen here in this step, or in this reaction scheme that's shown here at the bottom, is that with the Gilman reagent, you can think about that as being, an ethyl with a negative charge, but it's going to attack at the beta position. So look what would happen. You would get nucleophilic attack, and you would form an enolate. Let's draw what that enolate will look like. So we're going to have our 6-membered ring. We have our enolate, and we're also going to have an ethyl group over here. Well, what's interesting is that you can take that enolate and you could treat it with iodomethane, and that enolate is going to be able to react, right, like this, and do an SN2 reaction to give you this product. So there's a 2-step process for adding an alkyl group at the alpha and at the beta position of an alpha-beta unsaturated carbonyl compound. Kind of cool, huh? And you have to know this. So we'll put this in here. Know that you can do that. What else? Here's a review of the reactions, right? David Klein always has a beautiful summary of all the different reactions that are learned in every chapter. First, we have alpha halogenation of a ketone by treatment with catalytic amount of acid followed by bromine, and you see that you end up forming hydrogen bromide. So this is an autocatalytic reaction. The next one is the HVZ reaction, or the Hell-Volhard-Zelinsky reaction, which is where we do alpha halogenation on a carboxylic acid. First step is to treat the carboxylic acid with bromine and bromophosphine, and then treat it with bromine and phosphorus tribromide and water. Sorry, guys, I'm tired. Anyhow, next one is the haloform reaction. Very important reaction in organic chemistry, the haloform reaction. As I told you, we even teach that in nursing level chemistry. So you can imagine it's a very important reaction. Haloform reaction, treatment of a methyl ketone with sodium hydroxide. Again, you could use bromine, you can use chlorine, you can use iodine, and then you hydrolyze that and you end up forming a carboxylic acid. So you have to start with a methyl ketone in the haloform reaction. Let's see, what else did we learn? We learned about aldol addition, and we learned about aldol condensation, right? Aldol addition is when we use sodium hydroxide in water. Aldol condensation is when we use sodium hydroxide in water and we heated it. We looked at the cross aldol condensation. We looked at intramolecular aldol condensation reactions to form a ring. The Claisen condensation and cross Claisen condensations to form beta ketoesters. And we looked at the Dieckmann cyclization, which is nothing more than an intramolecular Claisen reaction. You can even see here that you have alpha and it's a beta ketoester. Again, then we talked about alkylation. So we talked about thermodynamic enolates and kinetic enolates. We talked about the malonic ester synthesis and how you add 1,2 carbons and a carboxyl, and the acetoacetic ester synthesis and how we add 1, 2, 3 carbons and we form a methyl ketone. Storic enamine, what else? Michael addition. We looked at stabilized carbon nucleophiles, whether they be a 1,3-dicarbonyl compound or a Gilman reagent. And we talked about Michael acceptors. We talked about the Storic enamine synthesis, how you take a ketone and you form an enamine, which is not going to be as nucleophilic, and therefore we'll do a 1,4 addition as opposed to a 1,2 addition. And then finally, we learned the Robinson annulation. And again, kind of took me a little while to explain it, but the Robinson annulation can all be performed in one pot. So you just take your Michael donor, your Michael acceptor, and you react them together, and you can form a 6-membered ring like that. An alpha beta unsaturated ketone is what results. And those are all the reactions, I believe, that we looked at in this chapter. So 21.42, using cyclopentanone as your starting material, and using any reagents of your choice, propose an efficient synthesis for each of the following compounds. Well, the first thing I notice about this problem is that you have 2 carbonyls and they are 1, 2, 3, 4, 5 atoms apart. And so this is going to be a candidate for the Storic enamine synthesis. So what's the enamine that we would want to start with? Well, I think about breaking this bond right here. And so the enamine that you would start with would be formed from cyclopentanone, wouldn't it? You would take this and you would treat it with dimethylamine, a catalytic amount of acid, and you would remove the water during the whole process, and you would form this enamine like that. Then your Michael acceptor is going to come from all of these carbons here, won't it? So the Michael acceptor will look like this. You'll have a methyl ketone on this end, and then on this end you'll have something that looks like this. So our double bond here, there's our Michael acceptor. And then finally, in the last step, you'll treat it with aqueous acid, and you'll end up with your product. The next one is a candidate for an aldol reaction. Let me show you how I would do this one. So I think about aldol chemistry with this one, and I would break this bond here. Okay, so retrosynthetically, I would want to start with cyclopentanone again, and I would treat that in the first step with LDA, lithium diisopropyl amide, to form this enolate completely. Okay, now normally I always drew the negative charge on the carbon. You can do that, or you can draw it like this. Either way is fine. Either way is fine. So I'll draw it like this to be consistent. And then what if you treated it with benzaldehyde? Let me show you what would happen. If you were to treat this with benzaldehyde, okay, let me move it over a little bit here. Okay, the enolate is going to serve as the nucleophile, and you'll end up with this tetrahedral intermediate, which looks something like this. So we're going to have a bond to this carbon, and we're going to have a negative charge on our oxygen. We're also going to have a hydrogen there. I'm going to leave that out, and we're going to have our 6-membered aromatic ring. And then in the last step, since this is a good nucleophile, isn't it? Right? This is a perfectly good nucleophile. If we treated that with iodomethane, right? What if we treated this with iodomethane? Well, you can see it's going to react in an SN2 like this, and that's going to give us our final product. And those are the kind of, ways you want to tackle these types of problems.